Okay, good afternoon, everybody. So thank you very much to attend this new talk in the series of CASS talk organized by the IEEE Circuits and Systems Society chapter Rio Grande do Sul in Brazil. Today we have the great pleasure to have here Professor Maciej Ogorzalek, that is from Poland and former president of CASS. So thank you very much to accept our invitation. Thank you very much also to Małgorzata to accept to be the session chair today. So as I already told you, Małgorzata has also a nice set of works and also several works related to 3D integration. So she's the perfect session chair for the talk today. So I give the floor to Małgorzata to do the announcement of Maciej.
Thank you very much, Ricardo, and good morning, good afternoon, and good evening to all of you. I'm Małgorzata Chrzanowska-Jeskie, and I am greeting you from Portland, Oregon. It is my great pleasure to introduce Maciej and his presentation on 3D integration. He probably does not need any introduction, as he's well known as a researcher and as the volunteer in many organizations, but just to follow the form of these lectures, I will give a summary because his activity is so wide that I can only give the summary. Otherwise, I would be speaking, not him, all the time. So Maciej Ogorzalek is professor of electrical engineering and computer science, and he's also head of the Department of Information Technology at the Jagiellonian University in Krakow, Poland. He has many visiting positions, and among them in Switzerland, USA, Spain, Japan, Germany. Between 2006 and 2009, he held the chair of biosignals and systems position at Hong Kong Polytechnic University under the Distinguished Scholars Scheme. And in 2019, he was visiting professor at the Integrated System Laboratory at EPFL in Switzerland. He's author and co-author of over 380 papers published in journals and conferences proceedings, and a book on chaos and complexity in nonlinear electronic circuits. Maciej gave over 60 plenary and keynote lectures at major conferences worldwide, and he also served as the editor-in-chief of IEEE Circuits and System magazine from 2004 to 2007. And he was a member of the editorial board of the IEEE transaction on CASS Part 1, Proceedings of IEEE, Journal of Circuit Theory and Application, and also Nota, Journal IC Japan. Dr. Ogorzalek was the president of Circuits and Systems Society in 2008. He served as division director, division number 1. He was the member of IEEE Board of Directors in 2016-2017. He is also the member of Polish Academy of Sciences, PAN, and member of European Academy of Sciences. He's also a fellow of IEEE. Maciej gave so many presentations and has been working on this 3D integration, so I'm sure you will enjoy the presentation and we'll learn a lot of new things about where this technology is moving on. So Maciej, please, the floor is yours.
Thank you very much, Małgorzata. You didn't mention that I had the special pleasure of making several things together with you. We gave tutorials at ISCAS and tutorials at LASCAS conferences together, organizing the tutorial sessions. So I'm very, very pleased to give this talk today and also to see so many friends around. So I will
can do the screen sharing now.
Yeah. I just wanted to say I would like to thank also Ricardo for organizing this whole series of, does it work or it does not work? Yeah, something is coming. So I can switch to PowerPoint. Hope you will see the full screen now. Hope everything works, because at this moment I lost the control of the other screen.
It's
so
okay.
Again,
Perfect.
Thank you, Ricardo.
Thank you.
And as I mentioned, special thanks to Ricardo for organizing this, because in this strange time, it allows us to meet friends and also learn many new things. We cannot travel to conferences, so this kind of events is highly appreciated and very, very welcome by the community. Okay, so I will give you a glimpse of the domain of 3D integration. At the beginning, I will give you a short overview of the background, why we are interested at all in this kind of procedures or new approaches to integration or circuit design, integrated circuit design. And then we'll give you some examples of what is going on and what we expect in the years to come, as there is a lot of new developments almost appearing every day. At the beginning, I usually put a couple of slides about where I come from, so you can see Poland is right in the center of Europe here. Krakow, my city, is in the southern part of Poland. I work now 15 years at the Jagiellonian University, which is a very old long tradition university. It was second in this part of Europe. We for several years we moved to a new campus, so you see we have very good conditions there, and probably maybe you could hear about the university, because I think the most famous person who studied with us was Nikolaus Copernicus, or Mikołaj Kopernik, as you say in Polish, and he was a student at our university exactly in the years where Columbus went towards America. So in 1492, there are records of the university books that he was the student. Okay, so now let me go through the short introduction, or maybe not so short, but I would like to say a few words about the integrated circuits. So as you can see, the history is not so long. First ideas came about integrated circuits, putting everything on one piece of common substrate, came from an engineer working at Siemens in 1949. But actually, the main ideas were developed in two different places, in Texas Instruments and Fairchild Semiconductor. So there were two examples presented almost at the same time. So Jack Kilby demonstrated the first one in 1958. Robert Noyce presented his development in 1959. As you can see, Kilby won the Nobel Prize for this invention. Unfortunately, Noyce passed away earlier, so he couldn't get the award. And as you can see here, these two pictures show circuits. Well, everything is made in one piece of the crystal. The first attempts were in germanium crystals, and actually, very, very fast. It started from 4 bipolar transistors, as you can see on the top picture here. 10 years later, we had already 200 transistors on a single chip, and obviously since then the whole story became really like exploded in exponential way. I would like to draw your attention to one thing, because I will be talking about 3D circuits. So I would like to stress that from the beginning, circuits were built on flat surfaces. Since 1958-59, almost all developments that we have made in the domain were made on flat surfaces. And actually, here I would like to mention work of one person. As Małgorzata mentioned, last year I had the pleasure and great opportunity to spend some time as visiting professor in Lausanne, and then I discovered that part of the work was done by a person of Swiss origin working at Fairchild, Jagiellonian University, who introduced the concept of so-called planar circuit. So transistors were built in one semiconductor crystal, and he introduced the protection layer on the top of it. So silicon dioxide, and then Robert Noyce, who is thought as one of the inventors of integrated circuits, proposed to put on the top of the silicon dioxide layer a metal layer to make the connections. So photolithography was used, and since then, 60 years, basically we are doing everything on wafers. Here you can see for one of the examples, a huge ingot monocrystal of silicon on the left side. So nowadays the technologies are truly fantastic, and we can fabricate huge monocrystals of silicon. Then they can be cut into very thin slices, like the one presented in the picture on the right. And this is the basis. So it's a flat surface on which we build all the elements, all the transistors, all the necessary connections and everything on the top of this flat surface. Okay, so we build circuits on the flat surface. On the top of that, we use for 60 years basically we are living in the flat world. So various processes available for treatment of these planar surfaces are available. We have photolithography, deposition, oxidation, ion implantation, passivation, and so on. Also, we learned following the planar process of Jean and Robert Noyce, we created many ways of layered interconnects, and also we learned how to put the encapsulation on the top of it. It's interesting also to observe, and very often this escapes as an obvious fact, that almost all elements have rectangular or cuboidal shapes, and almost all in the connections are composed of rectilinear wires crossing at 90 degrees. There are some exceptions, but they are pretty rare, considering the volume of different integrated circuits that are fabricated. So for a long time, we are living in the flat world, and you can see the development over the years was just spectacular. So nowadays we have circuits that are composed of billions of transistors. They have many layers of interconnects put on this flat surface, and the areas are around 500 square millimeters and more. The person who was behind many developments, and he was both co-founder of Intel, Gordon Moore, he made a prediction or observation that the number of transistors is basically doubling every 11 months, and until now it still holds. Even more spectacular numbers of transistors that we can put on the flat surfaces is in the case of GPUs and the FPGAs. It's really amazing. So as you can see, there are even chips that have 50 billion transistors. These are made by Xilinx. Okay. So to put more elements on the chip, we are scaling down the sizes of transistors and the width of the interconnect path. And we are really approaching the limits of the technologies and also physical limits. Till when can circuit work? How small can we make disintegrated circuits and their elements? So many people are saying, that by 2021, there were some predictions you could see in industrial papers that the flat circuits will be dead by 2021, and they will switch to new type of approach, which is called the 3D integration. So circuits and elements of circuits will be put in three-dimensional space, not only on the flat substrate underneath. So if you look at the current technologies, basically we are approaching many limits. So size of the footprint of the integrated circuits reaches around 500 square millimeters. There are some bigger ones and even some huge ones recently, but the yield, the production yield is under big question mark. The cost of the chip also grows exponentially with the size of the circuit. Another limitation is the size. We talk now about the already circuits fabricated with 7 nanometers, quite amazing ones. 5 nanometer TSMC, for example, is using some technologies in 5 nanometers. Question is whether it's worthwhile to go lower than 5 nanometers into 3 nanometers. What is next? So obviously with this comes the shrinking of the interconnect path. So how many wires we can actually squeeze, because this has also there are very strong effects related to how small the width of the interconnect path is. And also we have signal delays as the wires become longer and longer. It's becoming a big problem. If we put more transistors on the chip, obviously they all dissipate, all the elements are dissipating power. So the power consumption explosion is visible. And actually we observe a bottleneck. Leakage power becomes a major problem. So even if the circuitry is not doing anything useful for us, the circuit is consuming power. So currents are simply leaking. And obviously, from the point of view of a designer, the complexity is putting new questions for the designers. And then once the circuit is designed, we have to test and verify that the circuitry is really doing what it's supposed to do. And this cost is just becoming the major problem here. Okay, where are the limits? I will go very fast over this few slides here. So if we think about it, the atoms of silicon in the crystal, silicon crystal, the distance is around 3.12 angstrom. Angstrom is 0.1 nanometer. So if we are talking about the technology which has the feature size of 3 nanometers, it's just 10 atoms across. Okay, so obviously it's a little bit, imaginary example, but we are really reaching the limits of single atoms. So the feature size, the sizes of the electrodes in the transistors are so small that in some respect they are becoming uncontrollable. So on the left, you can see a picture which shows another problem. If you are doping the silicon in some regions of the crystal, you will have, if the electrodes are very small, we cannot do really reliable doping. Second problem related with scaling, with making things smaller, is the interconnect. So on the chip, we have usually typically three types of networks. We have the power supply, we have the clock distribution, and we have the signal path. And so there are three networks. If you consider that we have 50 billion transistors on the chip, all of them have to be powered. So we have to supply the voltages to where they have to go, and this is extremely difficult problem. I put here, I found a nice picture showing that if you think about it, because we are talking about, flat circuits, so everything is on the flat surface. It's built on the flat surface, but actually there is a structure of the interconnect metal layers. We are actually building a very, very complicated metallic structure in 3 dimensions. So it's going up on the top of the silicon part, which contains the active elements. So we have to realize that even in this flat approach, we are actually making 3-dimensional construction. If we look into, for example, our iPhone, what you can see inside nowadays, this is a few years ago, the A8 processor, you can see millions of the structures inside. And this is the one which we still consider it's a flat one. But if we look at the distances here, this is truly amazing. The distances are nanometers, and we have this extremely complicated interconnect structure in 3-dimensional mesh. With the extremely complicated structure comes the length of the wires. Okay? So here is just an example to show you that with scaling, we are extending the length of the wires. So the more elements are there to be connected, the longer the wires have to be. So in the chips, on the top of billions of transistors, we need to make over 10 kilometers. But if you consider that the size, the size of the chip, of the piece of the silicon inside is around 1 centimeter by 1 or 2 by 2 centimeters, and you have 50 billion transistors inside and 10 kilometers of wires. It really sounds very crazy. So people are looking for new solutions, how to overcome and shorten the distances, because with the distances we are also creating, the longer the wires, we create delays. Okay, so this little table shows you the comparison of how long it takes to make one arithmetic operation or a register read, comparing with the signal transfer. So the ratio between the signal delay and operation delay shows a ratio around 10 or 15 nowadays. Okay? So the processor actually, the arithmetic units have to wait for the signal to arrive where they have to arrive. This is why we have clocking. Okay. What are the solutions? So now we are coming to possible solutions. So as I mentioned, for many years, following the prediction of Gordon Moore, we observed that we were shrinking the size of features of elements in all known technologies. And how much farther we can go, really we are reaching the atomic limits. The other solution is to talk about the architecture. So as I mentioned, it seems to be very, very restrictive that we operate on a flat surface and try to put things the one next to the other. So we are looking for 3D geometries, and I will show you that we are looking in many different directions here, because we are also looking, instead of making the electrodes of the transistor smaller, which means full control of the properties, we also make three-dimensional transistors, and also look for new architectures. Talking about the architectures, we are trying to put the elements, the active elements, also in three-dimensional space, not only on the flat layer. And people are also looking at completely new technologies. For many years, the majority of circuitry was fabricated in silicon, some germanium, gallium arsenide. There are few materials that were used, but we are really looking for something completely different. So here, and I think that this is really the part which is for young people most interesting. We really need to invent new types of elements in architecture. Okay. So when I mentioned that how much further we will go with scaling, how much smaller we can go, 2 years ago, we can see that major producers, foundries, are asking the question whether this is really economically feasible or profitable. So one of the big producers, global foundries, stopped the 7-nanometer chip development. So they said it's not economically viable to really invest more into technologies that are not necessarily needed. Another very big supplier of semiconductor elements and chips, TSMC in Taiwan, they are looking at 5-nanometer, and here FF means FinFET. So I will say a few words about this kind of structures. So different types of transistors, different architectures of transistors, and as you can see, the cost probably is very high, but they were estimating also what we really gain with this technology. So 7 nanometers FinFET, we are not really gaining very, very much. This is still significant, 10%, reducing the power consumption, area reduction 17%. But here, 5-nanometer versus 7-nanometer, we are again, there is some gain, it is significant, 20% is a big number here. But the performance is only 15% better. So this is why probably global foundries stopped the 7-nanometer development. Okay. One more interesting picture at the end. Look at the cost of development of a chip in new technology. So as you can see, to make from scratch design until fabrication of a 7-nanometer, say, processor, for example, telephone processor, the cost is around $300 million. Okay? But if we switch to 5-nanometer, the cost almost double, 550. And as you can see, there is a very significant part which goes into validation and verification. And obviously, we need the software and all different parts. You can see it here. So it really becomes extremely expensive. The question is whether there are customers who will pay for this kind of chips. So why develop? Industry is asking always the question: why develop or introduce new technology if we can deal with the cheaper one? So a few slides about three-dimensional solution for the transistors. Probably you have seen this many times, but I would like to just to point out three developments. So typically in silicon, we are fabricating field effect transistors, and for some time already we are making structures that are called FinFETs. So as you can see, there are electrodes, source drain here, that look like a fin of a fish, and we put gates around, so there's controlling electrodes around, so making them like sticking vertical like a fin. We have better control. If we do everything on just deposition by deposition on a flat surface, the areas are becoming very, very small. Here, the area and the control is much better. And last, here we have completely different type of transistor, which is the nanowire transistor, and put vertically. Okay? So we have the gate electrodes all around. It works like squeezing a pipe, a water pipe. So applying the electric field, we can control the flow of the current through the structure. So one of the some of the laboratory measurements. Look how much smaller they are. Okay? So here the diameter is around 1 micron. The electrode depth around 1 nanometer. Sorry, 3 nanometer distance here. So much smaller than any of the flat types, and the parameters are very good. So here we have a concept of a chip which could use the vertical nanowire transistors. Recently we had, if any of you were listening, the VLSI SOC conference sessions, we had a very nice talk by Ian O'Connor about developments in this kind of structures. So 3D chips, 3D structures. Look, we have something underneath and something on the top of it, but the active elements are put vertical between them. So we produce a different kind of three-dimensional structure. And talking about transistors, that's the last slide about transistors. A very promising way of producing very effective elements, also called nanosheet transistors. As you can see, well, several companies, Qualcomm, Samsung, are producing this kind of structures with the gates all around. We have like spaghetti type conducting elements, and these nanosheet transistors are really they have very promising properties and are becoming very widely used. So individual elements are now sticking out from the flat horizon of a silicon wafer, and we build the functionality because of the three-dimensional structure. Now, a few words about 3D architectures. The concept of 3D architecture basically, I think, came from the observation of architectural building design. So from a completely different domain. If you look at the houses, why we are building skyscrapers in the cities? Because the area is onto which we are building is extremely expensive. So we are trying to put many layers, many stories, one on the top of the other, just to save the space. And also at the same time, if you look at such a structure like here on the right, just few layers, 6-story building. If we talk about the interconnections in a building, we have all kinds of infrastructure. We need to put electric wires, plumbing, air conditioning, whatever you can imagine, to every point that is needed. Okay? So the interconnects going in a vertical way are much shorter. If I have to connect, for example, this DSP slice with the optical input-output, and probably in many cases we will have a much shorter connection. A glimpse of the structures that nowadays are commonly produced and very widely exploited. So we have the concept of system on chip and system in package. So here we have system on chip. We have 3 different parts like building blocks fabricated in one piece. Here they can be fabricated in different nodes. So if we have foundries producing different elements like memories and processing elements and any other, we can connect them, not only soldering them onto the flat printed board, but we can try to connect them into one chip. And here comes the concept of so-called 2.5D stacking. So 2.5 dimensional. It's not really 3-dimensional because we have the flat dies here. So the building blocks are fabricated separately. These are flat pieces, and we just put them in 3-dimensional structure, putting on a special type of which is called the interposer. Interposer here only serves to make the necessary connection between the dies, which otherwise would be very difficult to make. And then we have interconnects with the external world. And the most interesting concept is to put layers fabricated separately and connect them through the silicon. So in the previous one, the interconnects were between them. They were made outside, okay, through the interposer. Here, we make the interconnection through the silicon. So it means that we have to make very tiny holes and separate them electrically from the surrounding materials, put conducting pillars inside, so this vertical layer wires. They are called TSV, through silicon via. It seems to be very nice idea to do it, but the process is very difficult. If we talk about sizes of nanometers, so drilling or making a hole which is a few nanometers wide, with extreme precision, because the different layers the holes have to fit into one another in proper places. This is very difficult. It's feasible. And even more complicated structure here. We have the interposer, but also through silicon vias, imagination goes very far here. We can develop many different architectures. If we talk about the interconnects, we can make connections outside. We can put many layers, but put all the interconnects outside. It's like many older British houses that have water pipes outside. Next solution, we have the interposer. So many interconnections are made through the interposer, and then we have through silicon via. So many slices of chips put one on the top of the other. And some real examples that it's really feasible. You can see this kind of structures, and also the through silicon vias are feasible. Already in 2006, as you can see, the pitch was 5 micron. The sizes of the through silicon vias around 1 micron. This technology didn't advance so much because putting the through silicon vias that are made of different material than into what they are being built, like silicon, they introduce many unwanted effects. So there are mechanical effects because the thermal coefficients are different. So, for example, such a pillar, such a through silicon via can extend in a much bigger way than the silicon around. So this may cause cracks in the chip if the heat dissipation is very high. So we cannot make them without really developing a lot of thinking and very good methodologies how to design, because they are thermal effects, mechanical effects, also electric effects, because the movement of the electrons in silicon is being affected. But we can think about circuits of this kind, like shown here. We can build levels in different technologies, so we can have more advanced technology for microprocessor, less advanced technology for memory, and we can put on top of it, for example, sensors that do not require such a very high level of integration. Maybe I'll skip this few things. If you think about it, here the imagination can go very far, because we can imagine that we can put in different layers, we can put chemical sensors, biosensors, imagers, MEMS, RF circuitry, analog to digital and digital to analog. We can put memory, we can put processors, but also we can put energy scavengers or batteries and hyper-capacitors. There are many concepts. So bridging different technologies can really, in three-dimensional way, because on a single piece of silicon, this is not feasible. So here in 3D, many of these are becoming really at the grab of our hand. There are many important parts that are not available in silicon that could be introduced in 3D, the technologies. So we can build nanolayers, energy harvesting. We can also build integrated cooling and so on. We can also invent new types of interposers. So, for example, we can introduce what is called the smart interposer. And smart interposer can make also, instead of making introducing very long wires, we can introduce interconnects that are made using radio frequencies on chip. We can also introduce photonic interposers connecting to optical networks and many, many other things. Okay, so where we are at this moment. So this was the table I had for the lectures last year, but I added something here. So in the last month, you can see that we have already a Apple A14 Bionic. So the new chips that are used in Apple iPhones, they are fabricated in 5 nanometer technology. And some, as you can see here, these are quite interesting, because clearly, even from the description, you can see that there are 2 different technologies here. So we are actually building 3-dimensional structures with layers. Each of these layers is a flat one still, but we put them one on the top of the other, and we really reach something really fantastic. As mentioned, 5 nanometers is already in practice, so you can buy the chips. Talking about industrial developments, you can see here we have processor packages together with the memory on the top of it, which are linked into one package, one chip. So, for example, the several Intel processors, you can actually order them with different sizes of memory embedded together with the processor. AMD is also fabricating the same stuff, the same kind of circuitry. As you can see, they're through silicon via, so the DRAM dies are connected between themselves, and also they go into the logic die, which is controlling the whole thing, and then to the interposer with the GPU or CPU unit. Real examples. Now, I would like to say a few words about fantastic developments that are really booming recently. And they really come from the observation that was known for many years already, because most of our computers are built using the concept of von Neumann. So basically the processing part of the computer and the memory part where we store the data and the instructions also are separate. So if we are making any kind of data processing or calculations, we have to send the data from memory to the arithmetic unit, which makes the operation, and backwards. So store, recover from the memory. This was not a problem when the data sets were small, so there was not so big transfer here. But very fast, people spotted that there is what is called nowadays, people call it von Neumann bottleneck. So we cannot squeeze the data, or there are big delays like on this highway here, depicted in this picture in the middle. So there are bottlenecks. The data is traveling very slowly. The elements have to wait for one another, and so on. So we need, nowadays, everyone is talking about big data. So we need a lot of memory. We need parallel processing. So basically, we need new design concepts. And basically, we need new technologies. First attempt was done using so-called Harvard architecture, where the instruction memory was put separately from the data memory. So this speeded significantly avoiding this for some time the von Neumann bottleneck. And now what we observe is that people are proposing new solutions, new technology. So memories are going 3D. If you consider the data bottleneck in conventional applications, we have 10% of time spent on accessing the data, and 90% is given for computing. If we have very big amounts of data, these are, you know, like averages taken from many observations. For big data applications, like controlling the autonomous car, 96% is data transfer and 4% is computing. And also, there are many errors. So if you are sending, you know, data back and forth, there is a lot of possibilities of missing some bits of the data. So as you can see, for conventional applications, those misses are, there's a small number. If we have huge masses of data, there are many misses. So this is pretty recent. I think it started like 2017-18, first examples were demonstrated. So people came up with the idea that we can fabricate a single memory cell instead of making it flat, what is called two-dimensional NAND. We can extend the concept and make a three-dimensional NAND, and actually make many cells, individual cells on the same footprint. Yeah? So the same concept. We have the small area, because on a flat structure, every single memory cell requires at least 3 transistors, I think, if I remember well. They're the simplest development. And here, on a smaller area, we can put many elements, but fabricated in a different way. So the concept is similar to this vertical structure, which is controlled by electric field. So we can make many pillars, going through many sheets of material. So here, the concept is a little bit different than just putting the individual layers produced in different processes. Here we produce layers produced in the same kind of process, but just one on the top of the other. It's a little bit complicated because we need access to all the layers to control the declines. But on a small surface, we can fabricate what is called the three-dimensional NAND. And another concept, so basically now there are two competing concepts. It's called 3D X-point. You can see it's like a mesh here, and here we have those pillars, okay? 3D NAND. So it has been already shown that this kind of elements, they give us very fast operation. So we want to get the data from the memory and send the data to the memory, read and write operations very fast. So this technology allows to make it much faster than anything else. And here, another concept, Western Digital produces this kind of blocks, which really looks like a building, just in nanoscale. So we have individual memory cells that are just these tiny things that are around the pillar. We have many pillars, and we have a three-dimensional cube containing memory cells. And what you can see now, so this year, we already have memory chips that are over 1 terabyte in one chip, 144 layers. So we have 144 layers. So like putting arrays, one on the top of the other in one chip. So it's like having double meaning here. We are reaching new heights because this is really like an integrated skyscraper. It's done in a different way than just putting, stacking layers on the top of the other, but it is a three-dimensional technology. And the concept, and the producers of memory, they obviously, each of them is proposing a different way of making this three-dimensional structures. So Toshiba has a different one, Western Digital has a different one, Samsung, something similar to what Western Digital has and Intel has. So just to mention that we can come up with many different ideas here. Okay, some current and future problems, and I think I will not have much more time, so maybe at this part, a few more slides. I will end with that. So everyone is talking nowadays about big data and artificial intelligence applications. So it's pretty obvious that we have, on the one hand, very cheap sensors that are almost in every piece of machinery around us, even in an electric bulb that is giving light in my room. There's a chip which is inside. So we have sensors that are measuring light intensity, current flow, and we are talking about intelligent houses, intelligent cars, intelligent cities. Intelligence is a keyword which many people are using, but we are producing loads of data. So Samsung, as one of the producers of memories, make a projection. We are 2020 here, and they produced that by 2025 we'll have 175 zettabytes, which is just impossible to imagine the amount of data. But they were predicting that we have to process this year, 2020, 44 zettabytes of data. We are trying to embed really intelligence, so some kind of analysis of this data almost everywhere. And I put here a couple of slices that are cut from a different talk I gave some time ago, and just to show you how much smarter is the nature. But I found two interesting papers that were published already some time ago, 2012. And some scientists were studying the increase in brain size during human evolution. But there are interesting parts that are marked here. So the first one was metabolic limitation, the number of hours available for feeding, and the other factor was low caloric yield of raw foods, imposed a trade-off between body size and the number of brain neurons. So people only being more sophisticated, they were able to, nature was building our brain. And the second statement is the human brain consumes 20% of the total body energy, despite representing only 2% of body mass. It's truly amazing. So actually, we could observe an exponential growth of our brain because we were also smarter. Okay? So the brain was able to analyze more data. So in a way, this produced or influences better brain. If you think about it, because I would like to make a little comparison here. So human brain, around 1.4 kilograms, is mainly made of protein and water, 100 gram fat, and the remaining is, so 1.2 kilograms is just water. It uses 20% of oxygen, 25% of glucose, and consumes 20 to 25 watts of power. Remember that. 86 billion neurons. A lot of them in what is called cerebellum. And this is amazing. 10 power 14 synapses, interconnects. So we have processing units, neurons, and we have interconnect here. Very naive estimates gives us memory 10 tera, 10 bits per synapse. So it's processing 1 petabyte, 10 power 15 data. Speed, very small. So we are in our electronic processors, we are talking about gigabytes. Here is below 100 hertz. Times 10 tera, it's 10 petaflops. And typically we keep only 1% of active neurons. Okay. Now, compare with our brain. I see number of elements. We have chips, I have shown you, example 50 billion. So it's not so amazing. Okay? Here 86 billion. The same range. But interconnects in the brain is 10 power 14 synapses. This is one of the major problems. Interconnect still remains a major problem. So so-called fan out. So how like one processing block, how can we connect to other blocks, like in the neurons in the brain? On the chip, you basically do it only nearest neighbors. That's the typical architecture. If we want to connect far, this poses big problems. If you want to connect to each element, each processing element, to hundreds of others, it's not feasible. Power consumption in our chips, we can't compete. 20 watts in the whole brain, it's simply not comparable. So it's not the number of processing elements like transistors. Neurons are probably more complicated anyway, functionality is different. But the fan out, so the interconnect is a big problem. So if you want to deal with big data, processing huge amounts of data, we need to design better chips. And we can actually see many developments. In some of the lectures in the I think last month in this series, you could see several concepts. And in all these concepts, we can see one thing. So the AI chip horizon is really flat. Really nobody is looking into three-dimensional 3D chips. I just picked a few examples here. So for example, the Pascal processor, the Turing processor, and these are quite complicated. Okay? 18 billion transistors. It has so-called tensor core, very fast calculating. It has several different pieces inside. Or, for example, NVIDIA Xavier chip. So it has a CPU cluster. Inside it has a Volta GPU and a number of other things inside if you consider it. Everything is flat. probably maybe some of you have heard the talk of Dr. Graneveld a few weeks ago, and he worked for Cerebras, and Cerebras has produced something amazing, really, in terms of circuit design. So they have what is called the wafer scale processor, and it is a chip which is 56 times larger than in area than biggest the GPU ever made. 46,225 square millimeters. So if you compare with 500 square millimeter or 800 square millimeter for the biggest one, biggest processor is really amazing. Why they do it? Because they want to make like an inference engine. Basically, there is a huge number, 400,000 cores that make multiply and add operations that are needed in data analysis, in many kinds of data analysis. So it's around 80 times more cores than any known chip. 18 gigabytes on chip SRAM, and you can push the data 100 petabytes per second through the interconnect to make this calculation, this huge calculation. So this is like a dedicated machine for making big data operations, data analysis. But it's flat. Nothing here about 3D. So why everything still looks very flat, even in the latest development. So obviously one factor here is that for decades technologies were concentrated on flat planar structures. They are very, very sophisticated. We have really fantastic technologies that are working. So we know how to fabricate wafers, very high quality, very high purity. We have light-based technologies for all kinds of processing of these surfaces. We know how to do it. Very sophisticated, and it is at hand. I think the real answer why for those applications, like building 400,000 processing units, they are not building in 3D. The real answer is cost. Cost is the major limitation. Cost in latest technology nodes, very small feature sizes, and putting things on the top of one of the other is very, very difficult. So it requires extreme precision. The production yield is relatively low, so the cost grows exponentially. And on the top of that, there are other problems like heating problems and interconnect problems also. So finishing the talk, I would just mention what I think I'm too long now, so I will not try to finish at this point. Because for me, the most interesting things for the future is what is called heterogeneous integration. So how to connect together and build together pieces of circuitry that are built in completely different technologies. We are introducing, apart from silicon, in silicon we know many things, and probably there are some more to be learned, like the multi-level memories. But really, to make a significant step forward, we need to look at other technologies, and people are doing it. So In my opinion, heterogeneity is the key for future development. New materials apart from silicon, heterogeneous stacking is basically very, very little known, and possibly this will solve the problem of energy efficiency. So, for example, maybe some of you could hear talks of Professor Subhashish Mitra, who is introducing new technologies to three-dimensional chips, introducing carbon nanotubes. Carbon nanotubes are much smaller, chips are faster, and energy efficiency is much, much bigger. So in Stanford, they are running a big program concentrated on this kind of new developments, new technologies. So into the concept of 3D, we introduce new types of materials. And maybe this is one of the last slides. I found this amusing picture some time ago. So if you look at the CMOS technology, we are hitting the heat wall, the memory wall, the Gordon-Moore law, and overcoming is very difficult. If we want to do the big data or Internet of Things, we need something new. Better memory storage, maybe bio-inspired computing, in-memory computing. There are many new areas that are hidden. Here I have. I thought I put this picture somewhere. So this is the picture that Subhashish was so kind to let me use in the lectures. So we have many different technologies used here, and the future is just amazing. So beyond CMOS, we have new materials, tunneling, transport, wave computing. We have carbon-based materials, graphite, layered materials like molybdenite, and so on. But this would require a separate lecture, at least probably 2-hour or 3-hour lecture. So let me thank for your attention at this moment, and thank you for listening to my consideration. It was a great pleasure. If you would like to ask some questions, you can do it either by sending email or now online if Małgorzata allows me still to use a little bit more time.
Okay, I had just. Maciej, thank you very much for this very interesting presentation, and we'll try to do it virtually. Thank you. Thank you very much. I can see that. The people are joining me. Can you hear that? The applause. So thank you very much for taking us on this wonderful journey from the just having the few transistors on the wafer, and then becoming this unbelievable structures which are today. I think that we were very lucky to be on the journey and witness how this technology actually exploded, and who knows where it can take us. So I do have, I can see in the chat that there are some questions for you, Maciej. And the first one is actually quite long. I'm not sure if you can hear me well. I see some kind of echo.
I can hear you pretty well. Okay. I hope you heard me better.
Now we're able to hear you better. Okay, now I think it's better. So the question is from Richard Inbound. A long question, so I'll try to read it slowly. I'm interested in knowing if there are any physicists working on the research of new technologies or ways of innovate in the integrated circuit projects and development. And also, other areas of physics, like magnetism or light properties, are being considered to find other elements for replacing silicon, or even for changing entirely the way of chip or transistor works. And there will be the second part of the question, but I'll read it later.
I can actually read on my screen. I can read the question. So the first answer about the physicists working. Obviously, in the research teams, I would make a wild guess, but half of the teams have physicists. So there is a big number of physicists that specialize in different areas, and this is absolutely necessary to have them, because they really advance, the devices, the device level. And the second thing I didn't show here, I actually ran out of time, because I wanted to show you some developments where we have the energy scavenging, so the energy scavengers on the chip. And amazingly, a big part of this research is done by chemists, not electrical engineers. If you look for development or research results, you have to look into journals. You have to look in the journals like Applied Chemistry, for example. So my students, I always encourage them look into papers and journals and even books in different areas, related areas, like electrochemistry. I had several contacts with people who are electrochemists that work for developing supercapacitors on chip. So they built tiny nanotubes. They are able to fabricate millions of them in parallel, and make on square centimeter a capacitor of 470 or 0.47 farad on chip. And these are chemists, electrochemists, not electrical engineers. So, once more specific physicists are needed, and they work with us.
Thank you, Maciej. I think that Del Oglio mentioned that Steve Friedman, who you know very well from University of Rochester, is working on some aspects of what the question was about. I'm not sure if you've been in contact with him. He was mentioned.
How many layers TSMC is using? I am aware of chips that have 5-7 layers. Type FPGA, for example.
Okay.
So several FPGAs put together. I don't know. This is probably their secret anyway.
So the second part of the question from Clavis is: are the companies who manufacture integrated circuits researching a way of build this integrated circuit other than in a flat chip, perhaps curved, in order to continue increasing the number of transistors, but maintaining the distance in a reduced length? So different shape.
Are the companies who well, this is a good question. Actually, this kind of we are working on a kind of this kind of project where we try to look what we can gain, not using only the flat things. It's not obvious, but if we look around in nature, nothing is flat. Nothing is rectangular, nothing is cubic. So, nature has devised those things and data processing in a much better way. So we should learn from that. But I haven't heard about any companies doing it really. Research-wise, yes, I know some people who work on it.
All right, thank you very much. I think that we still have a problem. Nani, may I suggest that you mute yourself and we see if this would work it better, unless you want to ask some question?
I get a question, but that question. Can I just pose a question to Maciej?
Sure, of course,
Yes.
please, go ahead. And then I'll continue with the chat.
Sorry for the, and then I will mute myself. People talk a lot about logic in memory. How would the logic in memory be envisioned within a 3D environment?
Oof, good question. Actually, I think, Nani, that it's quite feasible. Seeing the latest developments in the 3D NAND structures, I think we are just steps away from building logic also inside. That's my vision. I don't see. I know a little bit your work and know what you are talking about, but I think that this should be feasible in not far from where we are. That's my belief. I have no proof, obviously.
No, thank you. We'll take it offline. It's great talk.
Okay.
Thank you, Maciej.
Thank you very much, Nani.
Thank you,
I
Nani.
appreciate that your time spending with us.
All right, so let me go to the next question. May I? So how is the 3D NAND memories design affected by the increase of wire length for data transfer, or is it?
No, actually, here with the 3D NAND, the data transfer is, and this is measured, so it's not just simulations or whatever. It's 100 to 1,000 even times faster because the structure is different. So we can read in parallel, and so the readout structures are much more sophisticated than anything we had before. So we can read out the whole pieces of this big scaffold that we see in the pictures. So this is a major thing. We can not only store 1 terabyte in single chip, but we can also make it the transfer much faster. I don't know if this really how this directly relates to wire length, because that I cannot tell. But from outside, what you measure is much better.
Thank you, Maciej, very much. And another question. This one is from Ricardo. What is your view about the progress of monolithic 3Ds?
Monolithic 3D is a very nice idea, but in my opinion, it's still too expensive. To really make progress, we need a major industry to step into this. Without that, to a large extent, in my opinion, this remains a little bit academic research subject, which is very valid, very interesting, but the realization is quite difficult. I know several examples, but transferring them really to mass production in industry is a different question. I hope that it will happen, but we need a good example which could take it really to bigger volumes of production.
Okay.
So
Thank you very much.
This is my appreciation.
Okay. Thank you, Maciej. And another question from Ricardo. And this is, well, I think that Ricardo, you mentioned that also Professor Hoda Abdel Zawdi is working as on those new devices.
Very nice.
So I think that she's been connected with CASS for quite a long time. So a question from Ricardo is, are 3D IC designs discussed in academia?
No, the question is not from me. The question is from Professor Hoda.
Oh, okay.
I
So,
just copy his question from YouTube to here.
oh, I see. All right. So this is the question from Hoda, actually. So are they discussed in academia?
You mean, I don't know what is meant here. Are we teaching the students 3D design? I'm not sure what it means in academia, because obviously many teams are research teams are working on 3D designs, and there are many PhD students that are working on 3D design. But for students in the normal courses, I don't think, I'm not aware of.
Well, you know, I might add something to that. For example, in my university, I do teach about 3D, and this is about the technology for the like 3D with through Silicon VS, and also I'm starting doing that for monolithics, and of course work on teach students about developing tools for designing.
But these are master level, or
this is
PhD level?
Starting from seniors to master and PhD levels. So what's the so another question from Professor Hoda. What is the current involvement of bio-inspired technology or implemented deep learning?
Well, this is a completely different area, and well, I think there's not, well, people are making experiments, obviously, because for a long time we are trying to copy what is done in a very nice way in nature. So, but implementing deep learning, I'm not sure I'm a good person to ask that. I don't know if anyone has implemented deep learning in bio-inspired technology, because this is obviously people try to make simulations, but technologically I'm not sure. I haven't heard any good results of this kind.
Thank you, Maciej. Are there any other questions? I don't see any more in the chat. So maybe I'll ask the question from myself. So you've discussed three aspects, 3D in the technology, which were transistors. We're moving toward 3D and all those new technologies. And then you talk about the architectures. And of course, you mentioned that the big bottleneck, the huge challenge are interconnects. Do you know if there's any new developments in the terms of technology for interconnect, architecture for interconnect, the maybe synthesis of the design to improve or reduce the complexity of interconnects?
Well, I'm aware of people working on the problem of fan-outs, because that's one of the major bottlenecks. So if we have a large number of individual processing units, how you can interconnect them between them. So this is a kind of problem that is looked at by several research groups. About the tools, well, I don't think I'm aware of any good new tools for designing interconnects. 3D interconnect is as you know, it's a big problem. So people, even if we look at those pictures when we have layers, so in many cases people were considering well, basically extension of existing tools that were created for two-dimensional circuits to 3D. There are some attempts. I know some people working on applying well, specific kinds of artificial intelligence algorithms. So looking at what on the loads of studies that were done in the past, how we can really maybe invent something for a new type of circuit automatically. So this kind of research I have seen as well, but not really tools that could be useful directly for real circuit designers like in industry. I don't know if it answers your question sufficiently.
Thank you very much for your answers. So I'm looking, there's no more questions in the chat. So I guess I will just go get back to Ricardo, who is in charge of all those events.
Thank you very much,
Thank you very much
for your help.
Thank you very much, Professor Małgorzata, to be the session chair today. I hope to have also a talk by you in the near future.
Thank you.
So thank you very much. So thank you very much, Professor Maciej, for this very interesting talk.